Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in chapter 24. An amount of charge is distributed uniformly throughout the rod as shown in the figure. The length of the rod is A equal to 6.6 centimeters and the line charge density denoted by lambda is 4.2 microcoulombs per meter. With respect to infinity, find the electric potential at a field point P which is in the y-axis with B equal to 4.8 centimeters. Remember that relative to infinity, where the potential is zero, the potential of a point charge at position R is kq over R. If you look at our problem, at the position x on the rod according to the origin, let us choose a differential charge dq in the differential length dx. This infinitesimal charge can be treated as a point charge. Therefore, the electric potential of dq at field point P, which is a distance r from dq, is calculated as k times dq over r. We can take integral of both sides. The left-hand side, that is the integral of dv, is v. And the right-hand side can be written as k times integral of dq over r, since k is constant. In order to calculate this integral, we have to find an expression for dq in terms of dx. dq can be written as lambda times dx, where lambda is the line charge density and dx is the infinitesimal length in the rod. According to the figure, r is calculated by the Pythagorean theorem as square root of x squared plus b squared. Now we can write these expressions into the integral. As you see, lambda is outside the integral since it is constant. The integral is over x. The endpoints are 0 and a. From the integral table, we can write the integral of dx over square root of x squared plus b squared as ln of x plus square root of x squared plus b squared. And the calculation gives, or simply k times lambda times ln a plus square root of a squared plus b squared over b, since ln a minus ln b is ln a over b. With the numerical figures, as you see, although a and b are given in centimeters, we don't have to convert them into meters, because all the units in the calculation match and centimeters are gone. Anyway, with respect to infinity, we find the electric potential at the field point P as V equals approximately 4.24 times 10 to 4 volts. Now let us check the result. We find V as k times L times ln of a plus square root of a squared plus b squared over b. Since the charge is uniformly distributed through the rod, the line charge density lambda can be written as total charge q over a. Therefore, we have k times q over a and the ln term. We can simplify the argument of ln as a over b plus square root of a squared over b squared plus 1. As the field point, which is represented as b, goes to infinity, and since the binomial expansion of a squared over b squared plus 1 is 1 plus 1 over 2 times a squared over b squared and the greater power terms, the term a squared over b squared is very small, which is approximately 0. Therefore, ln function becomes, at this point, let us write the Taylor series expansion of ln1 plus x. According to our problem, x is a over b. And because x squared and x cubed are very small, we can disregard them. As a result, we have x, a over b. A's are cancelled, then we get kq over b. This result is reasonable because at an infinite point, the line charge behaves as a point charge. Okay, this is the end of the discussion of this problem. Thank you for your attention. See you in the next video.